In this video, we're going to review the method of substitution to help us compute indefinite integrals. Before we do that, substitution really comes from the chain rule for differentiation, so we should begin by reviewing that. For example, if I want to differentiate sine of x squared, the chain rule says that I should get cosine of x squared again, but I need to multiply by the derivative of what's going inside that sine function, in this case the derivative of x squared, and the derivative of x squared is 2x. What that tells us for integration is that if I integrate now cosine of x squared times 2x with that little extra factor of 2x, its antiderivative should be sine of x squared. So it's the result of the chain rule that we can integrate to get back what we started with. In order to manage the calculation, in practice what we do is a substitution, and the letter we usually use is the letter u, and in this case the appropriate substitution is u is equal to x squared. I'm going to differentiate u with respect to x, and when I do that I get 2x. And let's reconsider our integral now in terms of this new variable u. It's cosine of x squared times 2x. So that's really cosine of u because I said that x squared was u. And the 2x is really the derivative of u, so du dx. And I'm integrating with respect to x, so I'm going to put the dx there again. So here's the original dx, and then the 2x was the du dx. What substitution says is essentially what the notation is telling you looks to be the right thing to do. You should essentially forget about x's, cancel out the dx's, and think about this integral just in terms of this new variable u. You should be integrating the simpler cosine of u du. And that's good because we know an antiderivative for cosine, it's the sine function, with respect to this new variable though, u. Now we don't really care about u, it was just a tool to help us make the calculation, so I have to go back now and look at my table over here. U is x squared, so I'm going to back substitute that, and I really have sine of x squared. So substitution is a way of helping us integrate expressions that look like this: a function of a variable u times the derivative of u, and if you're integrating that with respect to x, you should just replace it with the simpler integral f of u du. We went from this integral here with this derivative factor to the simpler one that didn't have that factor of the derivative there. In the next slides, we're going to look at some examples of applying this method of substitution in more detail. Let's look at the integral of x times the square root of 4 plus x squared. I'm going to let u be 4 plus x squared, the stuff that's appearing under the radical. I'm going to take its derivative, so the derivative of u, du dx, is 2 times x, just using the power rule. And in practice, we're going to write this in differential notation, so I'm going to multiply both sides by dx. Du is 2x dx. Now I look at my original expression, I don't see a factor of 2, but I do see the x here. So what I'm going to do is try to match what appears in my integral. I'm going to divide both sides of this by 2. And when I do that, I'll have 1/2 du is x times dx. And I like to put that in the box because it's just a side calculation. I'm now going to rewrite my integral, but in a way that helps us just see what's going on. I've got this square root expression, and then I have x dx. So I'm going to put that to the right, just to group them together. And the reason I did that is because it's the integral of the square root of 4 plus x squared, which is what I declared u to be, so it's just the integral of square root of u. And then I have this x dx. X dx comes at the cost of 1/2 du, so I'm going to substitute that to 1/2 du, and I now have an integral that only involves this new variable u. Now that 1/2 is just a constant, so I'm going to put it outside. The square root is just a power to the 1/2, and I integrate this expression, it's just a power form. So I go up a degree to 3/2 and divide by that new degree. Let's simplify. Notice that it's being divided by 3, so it'll become, the 2's will actually cancel here, so it'll just be 1/3. U to the 3/2 is the cubed root of u, or I'm sorry, the square root of u cubed. And then finally, you look at your table over here, u is 4 plus x squared, and so that's going to go back in there for u. And I'm just going to back substitute now to get our antiderivative, and we're done with the problem. Let's look at another example. Here I have 1 minus x to the 4th to the 10th power. And in the numerator, I have 2 times x cubed. I'm going to take u to be what's being taken to a power in that denominator, that 1 minus x to the 4th only. Its derivative is minus 4x cubed. I'm going to write that in differential notation, so I bring the dx over. And I now go and look, okay, do I have an x cubed in my expression? Yeah, I do right here, but it's got this factor of 2. So I want to make it look like 2x cubed here. To do that, I'm going to divide everything here by negative 2. And when I have it on the left, I'll have minus 1/2 times 2x cubed. And that matches now exactly what appears in my integral. So the expression is really 1 minus x to the 4th to the 10th. That's my u to the 10th in the denominator. And then the 2x cubed gets replaced with minus 1/2 du. And I'm going to put the minus 1/2 outside right away and just put the du up top on top of the fraction. This is really just the power of u now, just like the previous problem, no harder than the previous one. It's u to the minus 10th. I integrate u to the minus 10th. I go up to minus 9, divide by minus 9. I simplify the coefficient. It's 2 times 9 is 18, and the signs cancel out, and it's u to the 9th in the denominator. And then finally, go back and look at your table. U is 1 minus x to the 4th, and I put that in place of u. There's your antiderivative. Let's look at a couple more. Let's take u to be 1 plus 4x squared. I'm going to take u to be 1 plus 4x. Notice it's linear, so its derivative is just the constant 4. I'm going to write that in differential notation, so I'll bring the dx over. I look up on my integral, I don't see a 4 dx, I just see dx, so I'm going to divide both sides of that by 4 to get 1/4 du, and that will tell me how to exchange dx for du's. The integral now is 1 over u squared, essentially. But the dx comes at the cost of 1/4 du. Again, it's just a power. I go up a degree, divide by that new degree. Simplify the expression, it's 1 over u essentially. And then I put the 1 plus 4x, which is what u is, back in for u. And if you like, you can distribute the 4 through there, it'll be 4 plus 16x. Let's look at a similar example. Notice it's exactly the same, except I'm not squaring the denominator now. In fact, I'm going to take u to be the same thing again. The entire calculation is the same. And I'm going to do the substitution. It's now just 1 over u. And the dx comes at the cost of 1/4 du as before. Notice that this is the special power. It's the 1 over u, and its antiderivative is the logarithm. So it's 1/4 the natural log of the absolute value of u. Finally, I back substitute in. U is 1 plus 4x, so that goes into the logarithm function.